Hey again, it's Mrs. Gabriel. I'm going to pick up right where we left off. So last time I was showing you an animation and we started with me kind of modeling here for you the Hadley cells. And remember, that's rising air. Rising air forms clouds because of the adiabatic cooling. And then we talked about these high pressure cells, and high pressure moves into low pressure, which is why our winds are moving in this direction. Now, I already explained this in more detail before. This is that intertropical convergence zone, which is where these winds from the northeast and these winds from the southeast converge, okay, intertropical convergence zone. So the winds are deflected. They're not just going north to south or south to north to meet at the equator, which is what common sense would tell you would happen, because the Earth is spinning. And that's causing a deflection, or really it's like an illusion. It's causing this illusion to us that the wind is curving, but the wind is not curving. It's that the Earth is spinning. So we're going to take a look at that. So I'm just going to play this video. I think I'm going to play it just to the point where you see these people spinning on a merry-go-round
straight
kind of thing.
Across the spinning merry-go-round, but where will it end up? Will it be caught by the thrower? Will it be caught by the person opposite? Will it be caught by the person to the thrower's
Where do you
left?
think the ball's going to
Or
go
by the person to the thrower's
when she
right?
throws it?
Right, in your own time, throw the ball.
I got this.
And there it goes. Is that where you thought it was going to go? Okay, so then that's
So the
the
answer
deflection.
was D. It was caught by the person on the thrower's right. Our camera angles
This is
seem
what
to show the
happens
ball
with the Coriolis
bend in the
effect
air.
on Earth
So is
with
that
our
a camera
wind.
effect?
So the ball
or are we
represents
seeing
the
what they
wind.
saw?
Hang on, this couldn't get much more simple. The eye.
So people seem to think that the ball is curving or that the wind
Actually
is
happening here
curving,
is you
but
are
that's
throwing
not
this
what's
ball. You can
happening.
only
So
throw a
look
ball
what
in a straight
happens
line.
if they're
Can I clear
not
that up straight
spinning.
away?
They're not going around and
Even though
around.
it appears
That's
in
just
your
like
eyes
if
to
the
be
Earth
bending.
were not spinning.
So you throw the ball
But
straight.
they are
Still
spinning,
going straight, but
just
the
like the
table is
Earth is
moving
spinning
blue.
on its axis.
And all of
And
a
that
sudden,
causes
Look who's in
what
front of that straight
looks
moving
like
ball. And it looks like
the
it's
ball
bent
is
off to the
curving,
right,
but it's really
because you're
just
still
that
looking
we
at
are
the guy
spinning.
you're intending
It's an
to throw to.
illusion.
And that,
That
ladies
is the
and gentlemen,
Coriolis
is the
effect.
Coriolis effect.
Okay, so we've talked about convection currents, and we're modeling convection in class. You're actually creating convection currents in class, and you should be able to explain to your mom or explain to somebody or draw a picture of the convection cell we created in class and how it models all of these things and models this. Even though we didn't create clouds, we can still describe what's happening in our model. So going back to this, here's those Hadley cells. They would have been right in here. Here they are, the rising air. And here is the wind. That wind is always described in the direction it is coming from. So the winds that are moving from that high sinking air, high pressure air, into the low pressure equatorial region are coming from the northeast, and they're deflected to the southwest. Then the winds from this high pressure cell, just like the animation showed, are now being deflected here. And they're being deflected because of the Coriolis effect. So remember that your Hadley cells actually go up to about 30 degrees north and down to about 30 degrees south. However, when the Earth is in a different position on its revolution around the sun is actually beating more directly up here or more directly down here, which is why this Hadley cell zone where the air is rising actually shifts or migrates as the Earth's position around the sun changes. That's the ITZZ, which is the intertropical convergence zone. And then our polar cells, that's just North Pole and South Pole, those are also convection currents. And that's air that rises at 60 degrees, so it's rising here, just like a Hadley cell, and then sinks at the North Pole, and then rising air at around 60 degrees and sinks at the South Pole. And then there's ferrule cells in between. There are convection cells. They are one of the major forces that drive all our winds on our planet. So then we've talked about already how clouds form. And we talked about adiabatic cooling as the air is lifted, and then latent heat, how then it gets warm again, and then when it's warmer than the air around it, it's going to rise even more. So you should practice covering this information and quizzing yourself on it. Try and describe what's happening at a Hadley cell now, all on your own. And remember what I've been telling you in class and what I've been telling you in these videos. It's not about just looking at the diagram, understanding it, and saying, yep, I got it. It's about being able to explain it in your own words, but using the appropriate technical terminology. That's what distinguishes you in an AP class that gets the AP college credit from a student that's just taking a general ed environmental science high school class. So here's just another picture that I stole from the internet, because what are they going to sue me for stealing a picture like this? I'm not making any money off of it. And the reason that I like this picture was because it's showing you what happens when we get rising air, we get a lot of rain, and then we get a lot of vegetation. And then we have sinking air that's going to create high pressure system down here. Sinking air does not form clouds. It's going to be dry, and it's going to be cooler. So dry air does not cause a lot of productivity, not a lot of vegetation. And that's because it's a limiting factor of precipitation. So then we get our deserts here, and we get our deserts here. And then, of course, we have new convection cells over here where the moist air rises again, right around our 60-degree zone, 60 degrees in latitude. We're at south latitude here. And this is where you're getting introduced in this picture to the different biomes associated with this type of atmospheric circulation. So a desert is a biome. A tropical deciduous forest is a biome. A tropical rainforest is a biome. And that's going to all be in the next chapter, or in the next section of the chapter. So we went over the Coriolis effect. Remember that it causes objects that are moving directly north or south to deflect. And remember also, it's really just an illusion. The Coriolis effect is really just creating this illusion that the wind is curving, but the wind is not curving. It's that we are spinning. Okay, once again, I stole some more pictures just to give you an idea of what the winds are called, what direction the arrows are going in, and where they're going. You don't have to memorize all these arrows if you understand where the air is rising and where the air is sinking. And then you remember high pressure is the sinking air, high moves into low. Now these winds are called our northeast trade winds, and then we experience in our part, our latitude area, we experience the westerlies. A lot of our winds are coming from the west. Those are the westerlies, and we also have westerlies down here. And there's many other little trade winds in here. You've probably learned about them in middle school, like the horse latitudes and the doldrums, but we don't need to get into those details in class. And then just an FYI, we're moving at almost 1,000 miles per hour at the equator when we spin on our axis in our 24-hour spin. That's like crazy cool, don't you think? Okay, so we have our definitions of Coriolis. We have a description of prevailing winds. Those are the winds I just went over with you. And those winds are produced by convection currents and the Coriolis. Winds are produced by more than just one thing. And all wind is the movement of molecules from high pressure to low pressure. Okay, so I covered the rain shadow effect in class. I'm just going to remind you, it's also called orographic lifting. I don't know if that'll come up. It's not in your book, but I think orographic it means we're referring to something about mountains, orographic. So the rain shadow effect is where we have a windward side and a leeward side of the mountain. If you can remember what happens to air, just understand what happens to air that's moist. What happens when moist air rises and cools? If it cools, it can't hold as much of its water anymore. The water is going to condense. So we got adiabatic cooling here. And then latent heat is going to make it release a little more. But really that adiabatic cooling and that condensation forms clouds. So that lifting, orographic lifting on the windward side of a mountain with the moist air is going to have rain all around here. And the rain is going to produce a very lush habitat, lots of trees and plants. When that air is used up and starts sinking, it's going to not rain. Sinking air does not form clouds. We are what we call the leeward side of the mountain. That descending air doesn't rain, so we don't have any lush vegetation, and this side of a mountain is going to have like the desert effect. It's going to be very dry and very rocky. Okay, so why are we talking about the rain shadow effect? Because it's not as simple on global climate and global winds. When we start talking about local climate and local winds, we can be as local as a city, we can be as local as a little mountain range. So we have to be aware of where convection and little types of lifting of moist air can occur that changes the local climate and local conditions. And then remember when we go on the other side of the mountain also, we had adiabatic cooling on this side and we had adiabatic heating because now the air is sinking. So the air is descending and adiabatic heating is happening and with drier air. And these are all the things that we've been going over. So you can pause it and study them if you want, because I don't want to go over everything that I already went over in class. And then these are the answers for Module 10. I hope you quizzed yourself and did well. And then we went into ocean currents. So I just wanted you to be able to recognize the patterns, and the patterns have everything to do with, well, they have a lot to do with the wind patterns on the planet and the Coriolis effect. And then you need to understand a little about ocean circulation, because ocean circulation also dictates climate. And I want you to understand about El Nino and La Nina, which is part of the El Nino Southern Oscillation. By the way, right now in October of 2017, the National Oceanic and Atmospheric Administration actually think that we are headed into a La Nina winter. You should think about, what does that mean? Okay, so a couple of things about oceans you should have taken notes on, but what you should have taken the notes on are just like, what are the currents driven by? This is a great multiple choice question. They're driven by temperature, gravity, prevailing winds, Coriolis effect, and the locations of continents, which I've already talked to you about all this. And just like air, warm water can also expand and rise. So as water gets warmer by the sun beating down on it, it can expand. By water getting warmer, warm water put into cool water, it can rise. And then our gyres are our massive circulation patterns. And these are the big gyres right here. So we have a gyre near us, because Baltimore is right here. So this is the North Atlantic gyre. And then we have the Pacific gyre, and this is the Northern Pacific gyre. And notice that they are both going in the same clockwise direction. That clockwise direction has to do with our winds. So remember that we have this northeasterly winds. Those northeasterly winds are making the ocean currents be pushed in the same direction as the winds into that ITCZ. So we're moving clockwise here. This is all driven by those by the northeasterly winds. And then we have the opposite happening in the southern hemisphere, where we have these massive gyres that are all moving in a counterclockwise direction. And they are driven mostly by those wind patterns that I explained when we were learning about the different convection cells. Now, there's other things that drive ocean currents, which we're going to go over. So I just talked about the prevailing winds and the Coriolis effect. And the reason we have different gyres and not one big gyre here is because these continents are in the way. But we also have temperature and gravity. And the gravity can also have to do with salinity. So we're going to get to that. So those are other things that can drive this stuff. By the way, these little blue zones, those are called upwelling zones. Upwelling zones are very nutrient rich. It's great for catching fish. So upwelling zones that are great for catching fish are because of diverging currents. I'm going to show you more pictures of that. They bring nutrients that support large populations of producers. The nutrients are needed by the phytoplankton, and the phytoplankton feed off those nutrients, which we talked about in chapter 3. But we talked about it mostly in the terrestrial zone. Now I'm referring to the aquatic zone. And then if we have a lot of producers, we're going to have a lot of other fish that eat the producers. It'll be a very, very productive zone wherever it's upwelling in the ocean. This is where fishermen make money. So oceanic circulation patterns are the result of differential heating, gravity, prevailing winds, the Coriolis effect, and locations of continents. And each of the 5 major ocean basins contain a gyre, which I was just kind of pointing out each one to you individually. Remember, that's driven a lot. The gyres are driven a lot by those trade winds that I explained to you, mostly in the tropics and the westerlies at the mid-latitudes. So those westerlies also help up here. And then we have the northeasterlies right down here. Okay, so another thing that drives ocean circulation, that's the thermohaline circulation. Okay, so this is different than the gyres. So I need you to pay attention to where the water is warm, and they think this is one big belt. They followed this by putting little buoys and having the buoys follow it. There have been shipping containers that have dropped things like sneakers, and they've tracked the sneakers for years and years and years to see, like, where does this massive oceanic conveyor belt go? Obviously, it's not going to go when it gets cold. When the water gets really cold, like once it comes up here, it's going to sink. That's really important. We need it to sink because that sinking is actually causing the ocean to mix. And we need it to mix because if it doesn't mix, then we're going to have a very warm, salt-free zone and then a very high, dense, cold zone. So thermo is temperature, haline as salt, and it's absolutely important that this conveyor belt continues to mix the ocean water, or we're going to have very different zones, and one's going to completely freeze over, one's going to be too warm. And we need the cold water because cold water is what helps bring the nutrients to the phytoplankton. So we need to move the heat, and we need to move the nutrients, and we need the salt because the salt helps with density, and we need the conveyor belt to constantly be moving and mixing the ocean water. It's called thermohaline circulation. So what I would do, I just explained a lot of this to you. I would read this, and then I'd cover it, and then I'd test myself, and we spent time on this in class too, but that's what I think you should do at home. And if you just understand it, then you're going to be fine. Also, you should kind of pay attention to where your oceans are, just in case you don't already know that, and I think you do, but just in case. Read and study. So remember, El Nino, I told you before, stands for El Nino Southern Oscillation, and La Nina is part of this also. And this is where the wind and water currents actually change direction. And scientists don't know everything about this yet. We just know it happens. And when it happens, it kind of changes climate. So I'm going to read a little excerpt from the National Oceanic and Atmospheric Association about El Nino. Although the exact initiating causes of an ENSO warm or cool event are not fully understood, the two components of ENSO, which are sea surface and atmospheric pressure, are strongly related. During an El Nino event, the easterly trade winds converging across the equatorial Pacific weaken. This in turn slows the ocean current that draws surface water away from the west coast of South America and reduces upwelling of cold, nutrient-rich water from the deeper ocean, flattening out the thermocline and allowing warm surface water to build in the eastern part of the basin. The strengthening and weakening of the trade winds is a function of changes in the pressure gradient of the atmosphere over the tropical Pacific. Okay, so just look back at the picture here. So here, I want you to think about Peru. So when we have the trade winds going in the direction that they should be, well, what they normally do, and they're going towards the equator, that is moving water away from the coastline. When it moves it away from the coastline, it's not like we suddenly leave a void of no water there. Other water fills it in. That's the cold, deep, nutrient-rich water. So these are during normal years. During those off years, which we call El Nino, the trade winds actually change direction. They're pushing the water into the coastline, and it's warm water, so none of the cool water upwells. If we don't have any cool upwelling, we don't get nutrient-rich water, and nothing's going to grow in the water, no phytoplankton, and no fish are going to come because there's no food for them to eat. So we're going to go over this in another chapter, but NOAA predicts we are entering the La Nina stage during our fall and winter of 2017 going into 18. And some of the factors of La Nina and El Nino influence local climates. So we should be experiencing some weather conditions that are a little different from normal. So the impacts are in our continental U.S. during El Nino years, the temperatures in the winter are actually warmer than normal in the northern, like central states, and they're cooler than normal in the southeast and the southwest. That's during El Nino. During La Nina, which is what we're going in, the winter temperatures are supposed to be warmer than normal in the southeast and cooler than normal in the northwest. And you can look up all kinds of climate changes that occur as a result of this. And for those of you that just like to look at a bunch of words, and you know I don't let you just sit there and copy words and words and words in class, you can pause if you feel like it, so you can just get everything that I was explaining to you here in words. Words, words, words. And this was just a diagram and some words for you to understand upwelling, which I think you should understand by now. Downwelling was the opposite. This is downwelling. And this one is showing the upwelling of the cool, nutrient-rich water. So this is a normal year, like around Peru, and this is an El Nino around Peru. It's going to cause that downwelling because of the change in the patterns. So your Module 11 answers to those multiple choice questions are E, B, B, A, D. We're going to go into the terrestrial and aquatic biomes in class, but the things that you need to remember most about the biomes are like how you can see that the vegetation changes, because it's a lot about vegetation type. And think about trying to classify your biomes based on this table, which I shared with you and we're going over in class. But I'm not reading you all this stuff. This is kind of like, this is stuff that you just need to look for the patterns and it'll help you understand it more. Your terrestrial biomes are really categorized by the average annual temperature and annual precipitation. So know your climatograms, which we're going to practice in class, and your plant growth forms, like what types of plants grow with this type of temperature and precipitation. And then when we look at an aquatic biome, we're not really talking about these things. We're talking more about salinity, depth, and water flow. Like a river is different than a lake because their water flow is different. And then I just stole some images for you so that you have something to help you remember what these biomes are. What I like about this one that I stole is this is kind of helping you with remembering, oh, we increase in the amount of rain in this direction, we decrease in this direction. So everything here, these names go with dry air. And these are showing us decreasing temperature. So they're related. And we categorize them. And then what I would do is I would cover the colors up. This is how you study. Cover the colors up and then quiz yourself on which one of these belongs to which color. And when you're doing that, it's not about memorizing. Think about all the things we just learned about with the solar radiation that it receives during the year. Think about, is it getting the side of the ocean where it's going, like, is it near water where it's going to be bringing a lot of rain? Are the winds moving air masses over the water and onto it? Or are the air masses moving away from the land? That's going to be drier. Think about the direction of the wind patterns to help you determine what the precipitation and temperature is, and that can help you remember and predict what the climate is like, and then the rest is easy from there. So this is a climatogram. We're spending time in class on that, but it's all about the difference between the gray and the white, and we're looking at where our temperature falls below freezing and where our precipitation falls to virtually nothing. And then we look at which one of those are a limiting factor, which we spent time in class on this, but it's all about when's our growth period. So you can really tell a lot about a biome without ever looking at it, without ever being there, if you know when plants can grow there. Because if plants can grow there, animals will come and eat them. If plants can't grow there, or it's so cold that plants need special adaptations to survive there, or it's so dry that they need special adaptations because there's no rain and it's just a lot of heat. And you get this now. Think of evergreen trees like the needles. They have special characteristics. Well, all of it's covered in class as well. But start connecting the dots and looking for the patterns. All right, so these are your terrestrial biomes. And we'll go, I'm not going to give you a big presentation on this on the internet because I wouldn't do it in class either. Get to know your biomes. This is Mrs. Gabriel signing out. Good luck with studying. I hope you understood more. Have a good day, night, whatever.